Okay, so we have 2 lessons left in chapter 4. So that's today and Monday. So Wednesday, you guys will have a quiz on chapter 4, and you will love it. It'll be so much fun. No, I'm being very serious. So the last thing we need to look at is solving trig equations. So we'll algebraically solve first and second degree trig equations in both radians and degrees. We'll verify that a specific value is a solution to a trig equation. We'll identify exact and approximate solutions of a trig equation in a restricted domain, and then we'll look at the general solution to a trig equation. A trig equation is an equation involving trig ratios. So as an example, what are the exact measures of theta if cos of theta equals -1/2? And how is this related to 2 cos theta plus 1 equals 0? So we're going to see how this all works. But an important skill to solve certain trig equations is that you have to be able to factor. So we'll review some factoring of expressions involving trig functions. So example 1 says factor the following trig expressions. So the first one is sine squared theta minus 4 sine theta plus 3. So as we first start these, you might find it useful to do this by using substitution. If we let's say, x equal sine theta. That first term of sine squared theta is the same thing as the sine of theta all squared. It's just a way of writing it without brackets. So sine squared theta could be written as x squared because you're letting sine theta equal x. Minus 4 sine theta would be minus 4x plus 3. And now if you factor that quadratic, it'll be x minus 1, x minus 3, because -1 times -3 multiplies to get +3. They add to get -4. But now we'll put our sine theta back in for x. So it'll be sine theta minus 1 bracket sine theta minus 3. Those are the factors in terms of sine. And you can always check those. You can always check them by multiplying them out. Sine theta times sine theta gives you your sine squared theta. Remember, sine squared theta means the sine of theta all squared. It's just a way of writing it without brackets. The outer product would be -3 sine theta. The inner product minus 1 sine theta. -3 take away 1 is -4 sine thetas. And -1 times -3, it gives you your +3. So this is a strategy that you can use when you're factoring these expressions involving trig functions. Okay, but I mean, hopefully you can get to the point where you don't have to, but it's definitely something that you can use. Question B, in this case, there would be a common factor of cosine x. There's only 2 terms there, and both terms are divisible by cosine x. So to get what's inside the brackets, we divide each term by the cosine x. And cos cubed x divided by cos x leaves you with cos squared x. And then the second term, cos x divided by itself, gives you 1. So the factors are cos x, bracket 2 cos squared x minus 1. And again, if you multiply it out, you get what you start with. So let's look at question C without using that substitution. The front terms have to multiply to get 2 tan squared x, which means one of the terms will be 2 tan x. The other will just be tan x. The last terms have to multiply to get +1. But when we multiply out the 2 binomials, we have to get a -3 tan x in the middle, which will mean that both of these have to be -1s at the end. -1 times -1 gives you your +1. The front terms multiply to get 2 tan squared x. The outer product will be -2 tan x. The inner product -1 tan x. -2 take away 1 is -3 tan x. So it checks. Question D is an example of difference of squares. Remember the simple type of difference of squares you looked at back in, let's say, 20-1 was x squared minus 1. It's a binomial. Both terms are perfect squares, and there's a minus sign in between. It's the difference of two perfect squares. To factor that, the square root of x squared is x. The square root of 1 is 1. 1's a plus, 1's a minus. That's how you factor difference of squares. So we'll do the same thing for sec squared theta. Take away 4. That is difference of squares. The square root of sec squared theta will just be secant theta. The square root of 4 is 2. 1's a plus, 1's a minus. There's your factors. Question E. We've got a trinomial that we want to factor. The front terms multiply to get cosec squared theta. So you have to have each term being cosecant theta. The last terms multiply to get -2. And when you FOIL it out, you have to get a +1 cosec theta in the middle, which means the 2 has to be positive and the 1 has to be negative. And you could have the -1 in the first bracket, the +2 in the second. That doesn't matter. But those would be the factors. And again, you can always check by multiplying. Question F, there's a common factor there of sine x to take out. To get what's left inside the brackets, you divide each term by the sine x. And so there's your factors. So again, this is sometimes a skill that we need to use in order to solve certain trig equations. Not always, but some of them. So this first example says to solve that equation where theta is between 0 and 2 pi. So again, that's important. It tells you that your answers have to be in radians. And also that 0 is included and 2 pi is not. Give solutions as exact values where possible, which means that we're going to have to use our unit circle. So let's start by setting up the unit circle. We've got a pi on 6, a pi on 3, and we've also got a pi on 4. So at pi on 6, remember the coordinates are √3/2 comma a half. At pi on 3, they're the same two numbers, but just in opposite order. And at pi on 4, they're both √2/2. The tangent is found by sine over cos. So at pi on 6, it'll be 1/√3 or √3/3. At pi on 4, it'll be 1. And at pi on 3, when you go sine divided by cos, you're going to get √3. So we'll be referring to this as we solve some of these trig equations, because some of them will get values that are on the unit circle. So to solve this, we can collect all the sine thetas together. We can subtract 3 sine theta from both sides. This one will not have to be factored because you can use algebra to get sine theta by itself. So on the right side, the 3 sine thetas cancel. On the left, 5 sine theta. Take away 3 sine theta leaves us with 2 sine theta. Then we will subtract the 2 from both sides. Are you with us, Samantha? So on the left, the 2's cancel. And we have 2 sine theta equaling -1. And our last step is to divide both sides by 2 to get the sine theta by itself. And we have sine of theta equaling negative 1/2. We'll also be using our cast rule here because our solutions will come in the quadrants where sine is negative, which are the bottom two quadrants, quadrant 3 or quadrant 4. And our reference angle will correspond to the angle in quadrant 1 where the sine, the y value, is 1/2, which is the first stop in the unit circle, where theta is pi on 6. But our answers are going to be in quadrants 3 and 4 with a reference angle of pi on 6. So this is how you justify your answers when you get them. You show which quadrants you're in, as well as what the reference angles or angle is. The reference angle is always the angle between the terminal arm and the x-axis. That first one in quadrant 3 is pi on 6 past pi. That's 7 pi on 6. And the second one is pi on 6 short of 1 complete revolution. 1 complete revolution is 2 pi, or 12 pi on 6 minus the 1 pi on 6 is 11 pi on 6. So there's the two answers that we have. 7 pi on 6 comes from quadrant 3. It's a pi on 6 past pi. And 11 pi on 6 in quadrant 4, which is pi on 6 short of 2 pi. Now, you can always check your answers. You should never get these wrong. Because our angles are in radians, we need to be in radian mode. The left side of the equation is 5 times the sine of, let's check 7 pi on 6 first. So 5 times the 7 times the sine of 7 pi on 6 plus 2 gives us a value of negative 0.5. Just so happens that that value equals what the sine of theta worked out to be when we got it by itself. That's a coincidence. But the right side needs to be the same value. 1 plus 3 times the sine of 7 pi on 6. So we're checking an angle of 7 pi on 6 on both sides to make sure we get the same value, and we do. That shows us that our answer is correct. Remember, your answers are the values of the variable that make the equation true. So now we need to check for 11 pi on 6 as well. So 5 times the sine of 11 pi on 6 plus 2 is also negative 1/2. And now we need to check for the other one. 1 plus 3 times the sine of 11 pi on 6. We get the same value, negative 0.5. Okay. So we've just shown that these two answers are correct. So you should never get these wrong. The only thing that you might get wrong is maybe you'll miss an angle that works, depending on what the equation is. Most of our equations will have only 2 solutions, but there are going to be some that we're going to see that have 4. The other thing that can change your number of solutions is by what the domain is. In this case here, the domain is between 0 and 2 pi. But sometimes they'll change that. Maybe it's between negative pi and positive pi, or maybe between 0 and positive pi. So you always have to read that part carefully to know which quadrants you're going to be in, as well as what those angles might be. So this next one, we don't have to factor this one. We can get cosecant of x by itself by using algebra. Also note the domain. This time our answers have to be in degrees. And 0 would be included potentially, but not 360 because theta is less than 360. So to get cosecant x by itself, we would add 6 to both sides and then divide by 3. And because we don't have a cosecant button on our calculator, we always convert it into the primary trig function. The reciprocal of cosecant is sine, and the reciprocal of 2 is a half. So now we want to see where the sine of x equals positive 1/2. Okay, so again, the sine of x, the y value, is 1/2 if the reference angle is pi on 6. So like the last one, we're going to have a reference angle of pi on 6. But what's different here is which quadrants we're in, because now the sine is positive, and sine is positive in the top two quadrants. And our reference angle is pi on 6, or in this case, 30 degrees, because we have to give our answer in degrees. So 30 degrees is one answer. Our second answer, 30 degrees short of 180, is 180 minus 30, which is 150 degrees. So to check this one, we have to be in degree mode, because our angles are in degrees. And 3 cosecant x is 3 times 1 over sine x, or 3 over sine x. So in brackets, I'm going to go 3 divided by the sine of 30 degrees. Close the bracket on the 30 degrees. Close the bracket on that term. Minus 6 should equal 0, and it does. We also have to check 150 degrees. So it's 3 times the sine of 150 degrees. 3 divided by the sine of 150, subtracted by 6. So you see, you get 0, which is what the right side is. So that just confirms that those two answers are correct. So you should never get these wrong. You can always check them. This next one, we're going to have to factor this one. You cannot do any algebra to get tan of theta by itself, because you have a tan squared theta term and a tan theta term. So this is one of the ones that we're going to have to factor. The front terms multiply to get tan squared theta. So those two terms must each be tan theta. The last terms multiply to get positive 4. And when we multiply out, we have to get a minus 5 tan theta in the middle, which means you need a negative 1 and a negative 4. You can switch them around. That doesn't matter, because the front terms are the same. You can switch those two numbers around. It won't make a difference. So our solutions now come where each factor equals 0. And so for that first factor, that'll be where the tan of theta equals 1. For the second factor, that'll be where the tan of theta equals positive 4. So if we put our coordinates at 0, that's 1 comma 0. And actually, I guess we don't need that, because it's where tan of theta equals 1, which is a reference angle of pi on 4 radians. Right? Our answers have to be in radians, because the domain tells us that theta is between 0 and 2 pi. And the tan of theta equals positive 1. Tan of theta equals positive in quadrants 1 and quadrant 3. Quadrant 1, quadrant 3, with a reference angle of pi on 4. So in the first quadrant, it is pi on 4. And in the second quadrant, it's pi on 4 past pi. pi on 4 past 4 pi on 4 gives us 5 pi on 4. So that's those two answers. Nowhere on the unit circle, though, does the tangent equal positive 4. It doesn't mean it doesn't exist. It just means you can't write it as an exact value. But once again, it's a positive 4, so we can be in either quadrant 1 or quadrant 3. And now to find the reference angle for this, we're going to have to go second function tan of positive 4 in radian mode. Sometimes you need to use the calculator to find the reference angle because the value that you get, in this case 4, is not on the unit circle. So second function tan of 4 gives us our reference angle in radians. So I'm going to round it to write it down, 1.33, but I'm going to store that number into my memory. This is going to be especially useful when we're going to check our answers. So 1.33 will be the answer in quadrant 1. Because the reference angle is 1.33, but in quadrant number 3, it's 1.33 past pi. So I stored that number into memory slot A. If I add pi onto it, that'll be the measure of the angle in quadrant 3, 4.47 if I round to 2 decimal places. But I'm going to store that one into memory slot B, again, so that when I check it, it's going to work. So my answers here are 1.33 radians and 4.47 radians. Remember, with radians, you don't need a unit. Okay, so now, here's our check. If I'm checking first, pi on 4. Tan squared theta means the tan of theta all squared. So I'm going to open up a bracket. I'm going to put the tangent of pi on 4. Close the bracket on that. Close the bracket on the tan of pi on 4 so I can square it. Minus 5 times the tangent of pi on 4. Plus 4, that should equal 0. And it does. So pi on 4 checks. Checking 5 pi on 4. Checks. All right, checking 1.33, so I put that entire number into memory slot A. So I can delete the 5 pi on 4 and put memory slot, whoops, try that again. Memory slot A in there. Same thing for the other term. So the calculator says the answer is 3 times 10 to the negative 12. I don't know why it does this sometimes, but it does. So that's 0.011 times and then a 3. It's essentially 0. And then when we check the value we put in memory slot B, which was our 4.47, we get the same number. 0 or negative 0.11 zeros followed by a 3. It's essentially 0. So again, in this case, we got 4 solutions. Like I said, sometimes you're going to get 2 solutions, sometimes you're going to get 4. Sometimes you might only get 1, depending on what the domain is. So there's no hard and fast rule that we can use for that. All right, let's look at example 4. What is going on here? There we go. So example 4 says, solve that equation. And again, that's one that we're going to have to factor because we have a cos squared theta term and a cos theta term. So we can't get cos theta by itself algebraically. Also note the domain is in degrees this time, so our answers have to be in degrees. So in this case, our last two numbers have to multiply to get -2, and when we multiply out, we have to get a -1 cos theta in the middle, which means the 2 has to be negative and the 1 positive. Those two numbers can be switched around because the front terms are both the same. It doesn't matter where the -2 is or where the +1 is, but you have to have a -2 and a +1 so that you'll get a -1 cos theta term in the middle when you multiply out. So our solutions will come when each factor equals 0. And this will be where the cosine of theta equals +2 and where the cosine of theta equals -1. And if you try and do second function cos of 2, because 2 is nowhere on the unit circle, in degree mode, if you do second function cosine of 2, you get an error. Does anyone remember why? If you look at the graph of cosine theta or cosine x, so I'm in degree mode, so my window should reflect that. I'm going to go from negative 360 degrees to positive 360 degrees. On the x-axis, I'll put a scale of 90. Normally we go from -10 to +10 for our windows. And a scale of 2. If you hit graph, that's what the graph of cosine x looks like. It actually only goes as high as 1 and as low as -1. If I change my y min and max to negative and +1 respectively, and a scale of say 0.25, so I'm going a minimum of -1, a maximum of +1. That's the graph of cosine x between 0 or between negative 360 degrees and positive 360 degrees. It only goes up to 1 and down to -1. And sine does exactly the same thing. It's very similar to the graph of cosine x. It has the same max and min values. The only thing that's different is kind of where it starts. This is the reason why that the sine of every angle, as well as the cosine of every angle, will be a decimal between -1 and +1, inclusive. That's right, there's only one solution for this one, where the cosine of theta equals -1. The cosine of theta cannot equal 2 because the graph only goes as high as 1 and as low as -1. Same thing with sine. So that's why when we did second function cos of 2, we got an error. There is no angle, theta, such that the cosine of theta equals 2. The only way the graph of cosine of theta could get to +2 is if it's been vertically stretched. So now we're talking about transformations, or shifted up a certain amount. Then it could get to that value. But this one will not. So again, there's no solutions for that part. Our only solution is where the cosine of theta equals -1, and that is at 180 degrees. At 180 degrees, the coordinates are -1, 0. Remember, cosine is the x value. it equals -1 at 180 degrees. So to check this, again, we are in degree mode already. So I have to square the cosine of theta. So I'll open a bracket. I'll put the cosine of 180 degrees in there. Close the bracket on the 180. Close the bracket on the cosine of 180 and square it. Minus the cosine of 180 degrees. Minus 2. That equals 0. So it checks. Okay, it checks. Now, you could also do this graphically. You could check it graphically. So if I put this equation into my calculator, again, I'll have to open up a bracket so I can square the cosine of x minus the cosine of x, close the bracket, minus 2. If I hit graph, that graph only hits the, and I guess I could change my windows here because my windows now have to be from 0 to 360. My solutions to this equation are where it equals 0, where the graph equals 0, the x-intercept. And there's only one x-intercept, it's right there. And that is at 180 degrees. That's where y equals 0. X-intercepts are where y equals 0. Okay? I went from 0 to 360 because that's what we were told up here to use. At the top, the domain was between 0 and 360 degrees. So I went from 0 to 360 degrees on the x-axis. And my y, I think, was from -1 to +1. Okay? All right. So we'll do some more work on Monday, solving trig equations. Again, you're going to have a Chapter 4 quiz on Wednesday. And then we'll get into Chapter 5. And Chapter 5 deals with the graphs of trig functions. So we'll look more closely at the graphs of trig functions. I just showed you in the calculator what the graph of sine and cos look like. So we'll go revisit those again, see where those values come from, and then we're going to do transformations on them, just like we did in chapters 1, 2, and 3. We're going to vertically stretch trig functions. We're going to horizontally stretch them. Okay? We're going to shift them, and you're going to have fun. It's going to be very fun. And then we'll look at the graph of tan x. Tan x looks completely different than sine and cos. Okay? For example, if I just put tan x in here, we're not going to see much of it with the windows that we have right now. If I increase my y windows to -10 and +10, we'll see a bit more of the graph. But that's what the graph of tan x looks like. Completely different than sine and cos. But chapter 5 is just the study of these graphs of trig functions. Okay? So quiz on Wednesday on chapter 4. And so you should work on page 211, 212, questions 5 and 7. I'll post those solutions to Google Classroom so you can check. And remember, last day's assignment was due for March. Hang on one sec.